Welcome back. So I am here to introduce our next speaker. So Max Welling was a postdoc under Jeff Hinton until 2003. Dr. Welling is a research chair in machine learning at the University of Amsterdam and VP Technologies at Qualcomm. Max is also a fellow in the Learning in Machines and Brains program at CFAR. So I'd like you to welcome Max Welling up on the stage to do his talk.
Thank you very much. Yeah. All right. Yes, this is very bright, it's true. So it's a big honor to be here. And of course to congratulate Jeff Hinton. Let's see if he's already in the room. Yes, he's right there. So congratulations on your Turing Award, and it's richly deserved. That's how I wanted to say. So I'm going to talk today about some of the work we are doing on physics-based deep learning. And you'll see what that means. I first want to acknowledge a group of really fantastic collaborators. It's a huge privilege to work with these guys, and I learn from them every day. So it's Taco Cohen, who just finished his PhD on symmetry groups in applied to deep learning, Pim de Haan, Maurice Weiler, Berke Kechanoglu, and Roberto Bondesson. Most of this work is being done at Qualcomm or QVA. QVA is a sponsored lab by Qualcomm at the University of Amsterdam. So let me start by showing you an image of one of the pinnacles of physics, actually, which is the Standard Model. So in the Standard Model, basically all of physics is being reduced to just a bunch of particles, right? And there's particles for matter, there's particles for forces, and there's a whole bunch of sort of Nobel Prizes, this is even a subset, that is being awarded to the ideas that form the Standard Model. And for those who haven't heard of the Standard Model, for those who haven't heard about what the Nobel Prize is, the Nobel Prize is also known as the Turing Award for physicists. And it's kind of interesting that the physicists have also come to the sort of idea that physics is actually all about information processing. So if you, it's hard for me to read this, but this is a quote from John Archibald Wheeler, and it says, "It from bit symbolizes the idea that every item of the physical world has at bottom an immaterial source, an explanation, that all things physical are information theoretic in origin." And so in some sense, there is a clear overlap between what we do in deep learning, which is at its core also information processing, and physics turns out. So what I'm going to try to do in this talk is to see if the deep ideas that we find in physics can be applied to deep learning. That's been the journey for me for the last couple of years. So we start with this guy, also a Nobel laureate. You all know him. When I went to visit CERN in Geneva here, there's this beautiful sort of statue here where all the important equations of physics are inscribed in it. And here's the one that is attributed to Albert Einstein, which is the general theory of relativity. So what is the general theory of relativity? It is actually based on a really, really simple principle. The principle is that acceleration and gravity are at heart exactly the same thing. You cannot distinguish between them. Right? If you look at, when you look at somebody who is in a rocket and does an experiment with a ball, and if the person doesn't know whether the rocket is moving or not, he or she cannot figure out whether it's gravity that's pulling the ball down or whether it's perhaps acceleration of the rocket. Right? And all of that basically results in this equation, which looks simple but is very deep, which describes how matter curves space-time. And the most important part of that is that it tells you how different observers will view the world if they move through different frames of acceleration. And this simple equation is true for all of those sort of different observers. That's what we call a symmetry. And the equation transforms covariantly, which means it doesn't change in the way we write it for all these different observers. And something similar happened with this guy, this is James Clerk Maxwell. He developed the unified theory of electromagnetism. And in that case, what happens is that what for one observer looks like an electric field looks for another observer looks like a magnetic field. And the only thing that you change is the speed at which you move past an experiment like that. So the symmetry, this idea of symmetries in describing different observers, is really a very fundamental and unifying framework. So I don't have to explain this very much. I'm just showing you a picture. This is a deep neural net. This is what this is all about, what we're talking today about. It's based on convolutions, which I think is the most powerful sort of form of neural net. And here's a little convolution. I'll come back to it later. But clearly, deep learning is all about information processing, just like physics, right? It's, you know, we put some information in, we process it, we dissect it in many different ways, and then at the end comes out a prediction of what's there in that information, in this first signal that's being put in. Now, how can symmetries play a role, right? If they play a role in physics, how can they play a role in deep learning? Well, there's one obvious one. If I take a particular image like this one and I rotate it around, it's still a particular skin lesion, irrespective of the rotation. So the prediction what this thing is completely invariant under the orientation or the position of where we see it. Same thing for digital pathology. So how can we build in these kinds of invariances in our deep learning structures? So we know already for a long time, and this was the idea behind sort of convolutional neural networks in the first place, that a convolutional neural network has this property, what we call equivariance, which is similar to this property that you write down an equation, and the equation doesn't change if I have a different observer. So here, if we move the observer relative to the digit, and we look at the internal representations of the deep neural net, you'll see that they just translate as well, right? So a translation of the input results in a very simple transformation of the internal representations of the neural net, and the end result is going to be invariant, the actual classification that this is a 4. Now, if you rotate it, something very different happens for a normal convolutional neural net. If you rotate this thing around, of course, it looks like it rotates, but you see all sorts of other things are happening too, right? It's not just the same thing that's rotating. You'll see that the activations and the activities are actually changing. Now, for a brain or for a neural network to look at this and to figure out that this is a rotated 4 is actually quite hard, because it's not just a rotation of the original input. It's kind of changed the activations a lot. And so looking at this and figuring out it's actually a very simple rotation of the input is difficult for this neural net. Now here's a more sophisticated version where you can see you know, sort of an image that we rotate around, and we see the responses of the original neural net if we stabilize it. So think of it as a camera that you look at it, and the camera rotates with the image, right? And then you can see, you know, what the responses are going to be. And this is, you know, it's changing all you know, when it's rotating. But this one here is actually stable, and that's one the algorithm that we like, which are the equivariant or invariant algorithms. Okay, so what is equivariance in a sort of more mathematical sense? It's actually not very difficult to understand. In a picture, it's super easy. So you take an image, if you translate or change the input under some kind of symmetry transformation, in this case, it's a simple translation. Then if we map it through a layer of a neural network, we get some filtered image, then there should be a simple relationship between these two filtered images as well. Sort of mathematically, you can think of it, this didn't come out very well, you can think of it as a function from x to y, which is the neural net, then phi x is symmetry transformation, and you want that you have some commuting diagram here. If you go first sort of filter and then translate, or if you first translate and then filter, you want to come out to the same answer. Okay, so that's what we call equivariance. And then the question becomes, okay, so we know that translations will give you, the convolutional neural net will give you equivariance under translations. How are we going to achieve equivariance under rotations? This was the first question that Taco Cohen and I asked ourselves when he started his PhD sort of 4 to 5 years ago. Taco came up with a really interesting solution to this problem. So say if this is a simple translation, or a simple convolution, then we're going to change that. And so we're going to do convolutions, but we just do 4 of them. If the group of rotations that we're interested in this case is like rotations over 90 degrees. So we're going to do 4 of them, and we're going to store the result in different feature maps. And every time when we've done one, so we've finished one, we then rotate the particular filter and then do it again. So we get these 4 rotated versions, if you want, of the same convolution. Now, how is that equivariant, you would think? So the way this is equivariant is illustrated in this particular image here. So you take an input image, like Mona Lisa, and then we have these 2 different feature detectors. One is an eye detector, and the other one is a mouth detector. So it's going to fire on this first image. You're going to see the 2 eyes, and you're going to see the mouth. But we also have these other rotated versions of these same detectors, right? This is these rotated sort of feature fields. But of course, they don't fire because they are orientation specific. So they only fire when they see the eye and the mouth at the right orientation. Now, if I do my symmetry transformation on the input, this is going to happen here, and I do it again, now what I see is that the second column of filters is going to activate. And you see that the actual detections have rotated because they're horizontal here and they're vertical here. But the other thing is you see is that instead of the first set of filters that have become active, now it's the second set of filters that become active. So this means under equivariance, 2 things happen. You rotate the activations and you cyclically move it through the 4 different orientations of your feature maps. Okay, so that's equivariance under rotations. And you can ask, okay, so why do we actually want this equivariance? What is so cool about it? There's 3 important reasons why equivariance is a good sort of principle for your neural nets. The first one is that it's like a convolution has a lot less parameters than a fully connected neural network. So you're doing a lot of sharing of parameters. And if you're doing sharing of parameters, you become much more data efficient. So that's happening here to a larger extent because now you don't have to train different filters for different orientations. It's just the same filter, but it's rotated by hand if you want. The other one is that, as I alluded to before, if you have this equivariance, then the next layer of the neural net is looking at a structure which is much simpler. So for the next layer to detect patterns again, it's much easier to look at something that's shifted or rotated than something that the activations are completely garbled up, right? And so it becomes easier to build representations on top of representations. And maybe related to that is to say that abstractions preserve symmetries, right? So if I take 2 faces at the first layer and I sort of map them through my neural net to an abstract face, and now if I would actually rotate, which means I would move in pixel space under my symmetry transformations, then I can guarantee that if I apply my neural net on these rotated images, I'll get to a rotated version of the abstract face. Okay, that's a nice kind of organizing principle to have in your neural net. So let's do a little test or a little sort of practice run here of how that works. So here is the 3 color channels for a image. Well, the first question we can ask is this 3 scalar fields, or is this 1 vector field? Is this a 3-dimensional vector field or 3 scalar fields? I won't do the hand raising here, but it's like 3 scalar fields, and the reason is if I rotate an image, what will happen is that this pixel is not a function of anything else than the pixels that live in this particular sort of image. It doesn't depend on the green or the blue image. So basically, the transformations happen inside these planes. They don't mix together. And so what we say is we can have this picture here that we have 3. We can chunk up the space into 3 blocks, and these 3 blocks under rotations they rotate into each other, but they don't mix. So there's these things living on the diagonal. Now this is different if I compute the derivatives, right? So if I compute the derivatives of an image, I get here the 2 derivative fields. Now if I start rotating things as here, right? I get now 6 channels here. Now if I rotate here and then I look at what I should do in this sort of feature field here, what should I do is I'm going to mix these things together, I'm going to mix these things together, I'm going to mix these things together, but I'm not going to mix these things together. So that's what's happening here. So I have these sort of sub spaces in my space, and they mix together under symmetry transformations using some kind of matrix here, which we call a representation of the rotation group, technically speaking, right? But they are block diagonal, so they don't mix among each other. And more generally, in group theory, what we say is we have representations of groups. We can choose them at sort of different sizes, and we say that a sort of sub group, sort of a space here, transforms under the representation of that group, but it doesn't mix between these different groups. And now the first relation to Jeff's work here is that this is actually a capsule, right? So we all know that Jeff is very, very excited about capsules. This isn't a capsule that is doing any routing or anything, but it certainly is a capsule in the sense that inside each one of these sort of capsules here, we encode the orientation of the object, and the different capsules, they encode different things about the object. They're different features, different qualities, or whatever of that particular object. But within a capsule, the representation that you have actually encodes the orientation or the pose of that object. And so you can do this more generally, not just for four orientations. You can actually make them steerable, which means that they work for every orientation. And then again, you can do a little experiment. You can run your neural net on sort of rotating input images, and you can see what the responses inside the neural net look like. These are scalar fields, and these are actually vector fields which are transforming. And then, unlike the images I've shown before, where the activations also start to garble up, here they very nicely sort of rotate under a rotation of the input. So if we do the trick again, where we have a camera, we rotate the camera with the input, and we stabilize it, we just look in the frame of the rotated camera, then what you see that nothing changes, which means that this thing is actually equivariant. It's like a visual test you can do. Okay, so that was the first part, which is, you can think of what I just said as the equivalent or the analog of special relativity, because in special relativity, we look at observers that transform, but we can do these transformations globally, right? We can do rotations and shifts, and in special relativity, there's Lorentz transformations, which also include speed, but still we have a global transformation on the entire image that we are doing. But then the next question that we ask ourselves, what is actually the equivalent of general relativity? Is there an equivalent of general relativity? And we banged our head against the wall for 3 years to figure out whether this was useful at all. And it's only quite recently that we figured out that it is. And there's actually very interesting, sort of set of observations or problems that you can apply this to. So the first thing is, you could imagine that you want to do deep learning on a sphere, right? Now, a sphere is a curved object, and there's actually no really good framework for doing deep learning on a sphere. And if you try to do it, you run into all sorts of problems, which I will tell you a little bit about more. So if you want to do sort of a weather prediction or something on the size of the globe, then that's already very interesting. You can also think about like a drone. So a drone would project, so think of it as having a lot of cameras around it, and it would project the image of the world onto a virtual sphere around the drone, right? So you have you see the world around you, like actually me too, right? I just see the world around you. If I move in my reference frame, the world in my reference frame rotates around me, right? So for a drone, that's also true. If the drone moves around, then basically he sees the world move around in his reference frame or its reference frame. So again, this is a sphere, and you may want to do deep learning on the virtual sphere, which is projected onto it. Another one is having sort of meshed objects, like in computer graphics or games, or in medical images. You often have meshed surfaces, for instance, of a heart, like a beating heart. Right? You might want to do deep learning on the surface of a beating heart. Right? That's a curved object, and so we can use this technology for that. So, and this is really related to general relativity. What I'm going to say, I'm not going to tell you much about the math, But the beauty is that it's exactly the same mathematics that goes into general relativity that is actually also going into these theories. And that's why I think there's a very deep connection here. And in fact, this was my thesis in '98. And if you look at it, basically, I drew this picture, which is, it's gravity in 2 dimensions. But we're going to do deep learning in 2 dimensions too. And so the way to think of that is you just cut out bits and pieces from Euclidean space, and then you glue these things together, these boundaries, you glue them together. And then what happens is if you shoot a light ray, it stops here because there's nothing here, it doesn't exist. And it pops out here, but then under a different angle. Right? So that's all, and that's because there is particles here which curve space-time. And of course that's very similar in 3 dimensions where you have some kind of heavy object which curves the space, and then sunlight will also curve in that space. So the problem in curved spaces is that you cannot really define a convolution very easily in a curved space-time. So what do we do, let's say, in a flat space-time? We have some kind of filter, and we move this filter to every other place, right? And then we do an inner product with the underlying image, and then we store the result with the next layer. That works if the space is flat. It doesn't work if the space is curved, because then what happens is if I go over one path, or I go over another path, then the orientation of this filter is actually changed, it's rotated. Right? So if I take a sphere, you can do this at home. I take a sphere and I take a vector on the sphere, and I move it along a path like this, and I come back, then actually it's parallel transport of that vector. Then the vector has a 90-degree angle with the one that you left behind, the one that you started with. So there is no single reference frame in which you can define that particular filter. And you can show this here maybe most easily if you triangulate that surface and you flatten it. Then what's happening is that there is going to be at the vertices, all the curvature is located at the vertices, and you can model that by basically cutting out a wedge from that space, and then you can simply see that this space doesn't exist anymore. So if I move it around and then I identify, go from here to here, it jumps, but I have to also rotate it, right? So there's no single reference frame in which we can do this, and in general relativity, basically, what people solved it is to say, well, we have reference frames everywhere. Every observer has its own reference frame. So wherever I am in my space, everybody has to have its own reference frame. And the only way that we can make sense of this is if I talk to my neighbors, I basically say, okay, I'm in this reference frame, you're in this reference frame, I'm rotated relative to you by a certain amount, and so I can match and compare my results to you. But this doesn't mean that globally, if you circle around, that things are well defined. Okay, so what I'm going to try to do now is illustrate in the simplest possible case how you would do convolutions on curved manifolds. And the simplest case is a cone, so that's one of these patches where we have all the mass or all the curvature concentrated at a point. So we now know how black holes look like. This is the first picture of a black hole digitally made, so I put it here, and we can imagine that the black hole basically creates this curvature. Now a cone is a special case because the cone is actually flat. It's only curved here at this peak here. And the way to handle it is to basically say, okay, I'm going to cut out of this space. I'm going to cut it open here, and I'm going to lay it flat on the table. And then in this case, the mass of the black hole was such that they had to cut out, let's say, half of that's a 90-degree angle. But now something really strange happens, right? Because if I take my little filter here, here's my little filter, and if I move it, again, if I move it to here, it will have to rotate. There's nothing really happening. It's just because, if I would have cut it open here, you wouldn't have seen it even. But if I move in this direction, and if I move in this direction, then the result is going to be discontinuous along this line because it's being rotated as I go along. And so there's this funny discontinuity in this convolution. It's not there's nothing physical or nothing. There's the signal below it isn't actually discontinuous, but because of this weird phenomenon, it looks discontinuous. So I need to solve that. Okay, so the way we're going to do it is we're going to introduce, as I said, local coordinate frames. So we're going to introduce, observers in space, And everyone maintains their own coordinate frame. So I've cut out, 3 charts here, 3 coordinate frames. And this one here is chart 1, and this is chart 2, and this is chart 3. So then the next step is, this looks a little daunting, but the next step is to then actually define a convolution on an arbitrary manifold. Of course, now this is actually a little bit technical, but the way we have to do it is as follows. If you don't follow this, just sleep through it. It's not a problem. You can understand the rest of the thing, the presentation. But here's a point P. Right? In order to do this convolution, we're going to draw a vector in the tangent plane of that P. And then that's kind of like shooting a geodesic. So it's like you throw a ball in this direction, and it moves over the manifold for a time unit 1. And then where it hits, that's the point Q that you're interested in. And that's the point that you want to do a convolution with. Then you do what's called parallel transport of the vector field. So this is your activation field or your feature field at this point, which is the signal on the object. And you're going to parallelly transport it up to P. And this parallel transportation sort of takes the vector and moves it. But at the same time, these two guys may have different frames. So you also have to compensate for the frame. So it's all in this particular matrix here, which moves it and matches the 2 frames together. And then finally, I have my vector here. I place it at this point V, and I do it for all these points around it. And then I do a convolution in this tangent space. I do a convolution with this kernel or this filter K. And this is basically what this is written out. Okay, this is a bit complicated, but that's what the algorithm has to be. And then finally, in order to establish equivariance, you need to solve a particular equation that you can derive. For the physicist, this actually looks a lot like a gauge transformation. So you actually do have, gauge fields are actually transformed in this particular way. And you have to solve it. It's a linear equation in K, so it's not super difficult to solve it. And then basically, if you go from 6 dimensions to 6 dimensions, you'll get like a field of operator or filters that looks like this. Now you see every color here is a different, every shade of color is a different free parameter that you can choose. But it's not, there's not entirely free, because you see that this object appears here, appears here, appears here, and then it's rotated around. So there is a lot of sharing of parameters going on in this kernel that we have here. How you get to it, I won't explain in more detail, but it is by solving this particular equation that you can derive if you want to maintain equivariance. Okay, so then the gauge convolution looks as follows. So here you have, let's say, 4 filters that you're going to do your convolution with. Here's my 4 filters, each under 19 degrees changes. Now, if I take this filter bank and I move it over this edge, over this arbitrary cutout, then they will all rotate. And here I just move them, as I would do on a flat piece of paper. So I would just translate them. And then again, you'll get this weird discontinuity here. In this case, the results look different because these filter banks are rotated. But there's not a problem, because this guy could just tell to this guy, okay, I'm in this frame, you're in that frame. So the way we should compare these results is basically by rotating our activation maps and by cycling, this guy should go there and it should rotate. Now that's exactly the same that we saw in the group convolutions. It's exactly the same operation for equivariance, which is you rotate and you cycle through the 4 feature maps. Now that's the whole story in some sense, and you can apply it to an icosahedral, which is an approximation of a sphere. So here's a sphere that is approximated by flat surfaces, and then the curvature is isolated at these points here. And because we can approximate it this way, we can do the convolutions extremely efficiently, just as efficiently as a normal convolution. So these are the charts. So this is like one big sort of chart, but then if you move from here to here, you have to do these funny rotations if you go along. If you go like a circle like this, you actually rotate your feature maps. And then you can do some application. We did some experiments, for instance, on segmentation on curved objects. So here we have a weather map, and we were detecting the storms that we're developing in these weather maps. And you can do this very beautifully and very efficiently with this framework. And here's another indoor scene, 3D indoor scene that we can do segmentation on. I won't bore you with the bold numbers, but it works fine. Okay, so that was the first part of my talk, and I want to spend the last 50 minutes. So this is all well established, it's published and everything. Yesterday, when there was the fireside chat between Eric Schmidt and Jeff Hinton, they were asked about what keeps them awake at night, right? Okay, so here's my answer. This keeps me awake at night. It's not published yet, but it is, I think, extremely interesting and extremely promising. And I'll just talk to you about it and see where it goes. I cannot say it's I sort of have a quantum supremacy in deep learning, as Google claims with their quantum computing, but it is a very interesting direction, in my opinion, to look into. So these guys are, of course, famous physicists now for quantum mechanics, Schrödinger and Bohr. And that's the Schrödinger equation you saw there. Okay, so interestingly, quantum mechanics is not all that different from what we already know. And why not? Well, we already know how to deal with probability vectors or probability fields. Right? In graphical models, when we write down a probability field, we have a whole bunch of variables and we write down probabilities over them. Probabilities are, are real numbers and they're positive and they add up to 1. In quantum mechanics, they have replaced that by another object, which is a complex object, psi. It takes values in complex values. The probability is derived by looking at the absolute value squared of that. So you can think of this as a subprobability, or a probability amplitude, as some people call it. So if you take the square, you multiply it with its own complex conjugate, and so you get the square. That thing is a probability, and that has to be larger than 0. And that's actually, when you do a measurement, you compute that in order to figure out what the probability is. And these add up to 1. Now, the big difference is that if you have a probability of 1 in a classical system, what's happening is that you're certain about the state of the world. You know everything about the state of the world. And if I ask you any question, you can answer it with certainty. In quantum mechanics, so we call that your information is maximal and complete, right? Now, if you look at it for a quantum system, if you have this certainty, for instance, you know where the particle is with certainty, your information is maximal, but it is not complete, and it cannot be further completed. Because if I ask you then a question about the velocity of that, you're at a total loss. You know, that's the Heisenberg uncertainty equation. And so here, there was another difference is there's no interference possible here because you just add up positive numbers. But here you can have cancellation, so you can have negative numbers and they can sort of cancel with each other. So if you look at a particular experiment in quantum mechanics, it's a sort of version of the two-slit experiment. You take a source, you have a particular wave, sort of a photon or a light that you emit, and it goes to a half mirror. Some of the photons will be rejected. You will be reflected here, some of them will get through. And then here's another mirror, and then it bounces back and goes this way or this way. It is again a half mirror. Now, if you measure where the photon is, so now let's imagine you're emitting light, but that a photon at a time, one photon at a time. Then in our classical way of thinking, it has to go either pick this path or pick this path. And if we measure where it is, right, then it's true that it looks like classically, it behaves classically, because then it goes here, and there's a half probability of coming here, and there's a half probability of getting there. And you see sort of detections in both of these. But the big difference is if you don't make this observation here, then you could classically still think that it either takes this path or this path. But then if you do your measurements, the weird thing is it can now interfere. So this path and this path can interfere, like light as a wave. And you can only sort of, this might just interfere to 0 and this to 1. And so in some sense, the photon, even if it's a single photon, you know that it's like single photons that come out. If it takes this path, it needs to be aware that this path is there somehow and interfere with it. So in terms of Bayes' rule, this is familiar to us, right? So it's like the probability you arrive here is the probability that you're here, plus the probability that you get along this path, plus the probability that you're here, and from here you reach here. Now the bizarre thing is that in quantum mechanics that does not hold. So in quantum mechanics, this funny Bayes' rule here does not hold, and that's exactly because of the interference. Now, this is philosophically very interesting. And here's why. So if you know about the Dutch book argument, the Dutch book argument says that you can bet on particular sort of place money on particular bets. And there's only one way to do it right. So there is only one way to assign probabilities to the probability that you're winning. And that's basically, those probabilities follow Bayesian statistics. Now, the same thing is true. So you can also set up the same Dutch book argument for quantum mechanics. And it turns out that theory of statistics is also consistent. So it's really bizarre. It's a different theory of statistics that is also consistent in the Dutch book sense. And so there's a bunch of people, they call themselves cubists or quantum Bayesianists, that basically think of quantum mechanics as a state of knowledge, not a state of the world. And so why is this interesting? So you can think of this as that you're interested in in running things on a quantum computer, and I am interested in developing algorithms for a quantum computer. But even classically, this is interesting in my opinion. The other thing you might think is, well, you know, quantum statistics is really developed for what we call Hilbert spaces. But we already deal with Hilbert spaces, right? I mean, when we write down a graphical model, you know, we already write down these energy-based models, let's say, which is an energy for every possible configuration of bits x1 to xn. And it's an exponentially large state, right? There's one energy assignment to an exponentially large set of these bit assignments. That's very similar to quantum mechanics, where you write down a probability that's more like this. And so let me digress a little bit into this, because actually when I started my career, let's say in machine learning, I went to work with Jeff. And I started to work on these energy-based models, right? So this was my first, basically, my first assignment or my first sort of topic that I was working on. And sort of in that time, you know, I learned about this equation, which is also a physics inspired equation, if you want. So this is the equation for the free energy that was written down by Radford Neal and Jeff Hinton. And it's basically the single equation that since then has influenced my work the most. Because this, you know, if you know about it, but there's an energy term, which is a lot of probability over all the unobserved things. You take the expectation of the unobserved things, which are latent variables in the parameters, and there's an entropy term. So the energy minus entropy, which is exactly what the free energy is in physics. So I've used it for training graphical models and belief propagation. I've used it for variational autoencoders and for Bayesian deep neural networks. So this is the one equation that has influenced my work most, and it's also physics-based. And I learned it first, you know, in the first years when I started at Gatsby Unit. Okay, so a little bit more on finishing the quantum computation case. So a qubit is different from a normal bit in the sense that it's more like a sphere. It can take values on the surface of a sphere. It basically is a linear combination of the states 0 and 1. These are complex numbers, and they have to add up to 1. So it's a richer object than a normal classical bit. And the other thing which is classically doesn't happen the way it happens in quantum mechanics is entanglement. So you have these entanglers, which are unitary transformations, which take the states of these bits and they turn them into some linear mixture of those. Anyways, it's going to be basically a combination of all of the exponential number of states that you can create this way. Of course, in graphical models, we do something like that too, where we assign probabilities, a probability distribution to every possible joint state of the bits. And you know, a wave function is nothing else than just one giant probability distribution for all of those states together. So then what we started to do is we started to build neural networks, convolutional neural networks that we can run classically on a computer, but when we run it on a quantum computer, get exponentially more powerful. So what we do is at the input, we give it sort of classical bits. So we basically say this is state 1, state 0, state 1, state 1, etc. And then we have these sort of these entanglers, which only took 2 or 3 of these bits at the same time, and we entangle them into a mixture. And if we do this, we can, if we take this to be the same, to be the same, to be the same, we get some translation invariance in this system. We can repeat this a couple of times. So after we do it this way a couple of times, every bit gets entangled with every other bit, but in a way that is still manageable in a classical computer, because we don't entangle everything jointly. Then we need operators like pooling, where we sort of discard some of the bits. Now, there's a couple of things that we've looked at. projecting them on a particular state, measuring them, tracing them out, ignoring them. There's all kinds of things that you can do here we're playing with. And then at some point, if you have been entangling in this space a lot, at some point it doesn't fit in your classical computer anymore. It would still fit in, in a quantum computer, but not in your classical computer. So then you would need to do a measurement. And when you do a measurement, everything gets projected back into a state which is disentangled and fits into your computer again. It has the other advantage that it acts like a nonlinearity as well. So you do this for a couple of layers, and then in the end, you measure one of these sort of lines, and the answer probabilistically is going to give you whether it's a cat or a dog. Okay, so we have trained these models. We can successfully train them on a classical computer, obviously, and we can get sort of on par with classical deep learning systems. However, the promise, of course, is we haven't explored a whole lot of operators which exist in the quantum literature, so there's a lot of room to maneuver, even classically. And in a quantum computer, we can make these entanglers very large, and we can be much more powerful in terms of that sort of computation. Okay, so then I've arrived at the last slide. So of course, we've done special relativity, we've done general relativity, we are working on quantum mechanics. So next up is, of course, quantum field theory, right? And in quantum field theory, we haven't started on this, but we know that quantum field theory is going to be the standard model of deep learning. That's what we really want. We're ambitious. We want to build the standard model of deep learning. So in these quantum field theories, there's particles, right? So we have the particle, the photon, and the gluon, the ZW boson, the electron, and the muon, and the fermion. And then in deep learning, I hope that we can also find the hinton, which is going to be the elementary particle of deep learning. I'm almost done. And in fact, I would like to invite CIFAR to build the Large Hinton Collider here sort of around sort of Toronto. I think it's going to be a wonderful investment to smash deep learning and models on top of each other. And so what are the properties of that hinton? In order to detect it, we need to sort of figure out what it does. So first of all, it has very high energy. This is good. It is highly speculative too. It may not even exist, but that's okay, because next week or next month, there's going to be a new idea, and there's going to be a new particle. And then we know what the particle is. It's also an extremely intuitive particle, actually. Yeah, you don't need any math to describe this particle. And it's also the only known particle which has humor, British humor, by the way. And it's also a very humane particle. This particle actually cares about other particles. And it certainly gives them inspiration as well. Certainly, Jeff has given me inspiration over the years as well. Thank you very much.